So we are going to start with lecture number 2 of electric drives course. In the last class, I had explained about various components in a drive system and how each of them play their part to ultimately make the entire system really respond faster as well as accurately. So today we are going to start with if we really want a drive system, how are we going to make a choice in our particular application? So the first thing I'm going to look at is choice of an electric drive. How we are going to make a choice of an electric drive for a particular application. This is the first thing we are going to look at. And second thing that I'm going to explain is what do we mean by 4-quadrant operation of an electric drive system? How do we really understand the concept of 4-quadrant operation? These are the two things that we are going to really look at today. Okay. So we said that a drive system consists of a power supply or a source, which is being processed by a power processing module. So let me call this as power processor. And from the power processor, whatever is the power that is coming out, the electricity that is coming out, that is going to go into the motor. And the motor is actually coupled with the load. The load is driven by the motor. And now we are going to have from the motor and load coupling, we may be sensing the speed and the torque. So I'm going to write here speed and torque. Both will be sensed. So we will have a feedback mechanism, maybe through sensor and so on. So this is going to be sensed by this feedback sensing mechanism. And this particular feedback mechanism is going to pass on whatever it has got as the input from the sensor, that is going to be passed on to a control unit. So the control unit is going to feed the control signal to the power processor. Depending upon if it is like an AC to DC converter with thyristor, then we may require firing signals for the thyristor. If it is an inverter with IGBTs or MOSFETs, then we will require gating signal for the IGBTs and MOSFETs and so on. Now, apart from sensing this, it may also sense the voltages and currents from here. So this may be voltage and current. Those may be sensed from here. And of course, the control unit should also have reference signals. So the reference signals may be speed reference or current reference or voltage reference, or it may have torque reference, anything. One of them may be the reference signal, or even two of them could be the reference signals, depending upon whether we have single loop control or two loop control or multiple loop control. All those things are going to play a role in deciding how many reference signals are going to be fed to the control unit. So this is essentially the sensor. Whatever we have shown here is the sensor or transducer, what we have. Now, there are different kinds of motors available in the market. There are different kinds of sources that are available. So how are we going to make a choice of an electric drive when we know that our application requires, maybe certain amount of torque and certain amount of speed? The range of speed and range of torque is known. First and foremost thing is we should know what kind of source is available in our particular premise. If it is an industrial drive, in our premise, what is the kind of source that is available? The sources commonly available in India, if you particularly see, it can be 230 volts, 50 hertz, single phase AC. Or it could be like yesterday what I specified about 380 to 440 volts, 50 hertz, three-phase AC. So any of these two could be the sources that are available. Another thing that may be available as the source could be if it is a DC motor drive which is driven by a battery, then it could be a DC source. Depending upon the battery rating, the voltage may be anywhere between 12 volts to maybe 24 volts, 36 volts, 48 volts. It could be 220 volts or even sometimes 440 volts. So we could have a DC voltage ranging from 12 volts to 440 volts. So if I'm going to have AC source available, then I have to make sure if it is a DC motor drive, then I might have to have a rectifier before feeding it to the DC motor drive. So the power processor choice and the source, both of them decide ultimately the kind of drive that you want to employ in your industry, and also in terms of what is the range of the speed and torque and power levels that you want to have. All those things ultimately have to decide the choice you make for your particular application. Normally, for any drive unit that is having less than 10 kilowatt, maximum 50 kilowatt, generally we use single phase. Whereas whenever we are talking about anything greater than 50 kilowatts, for sure we have to make a choice in terms of three phase. So three phase AC power supply is available in your industry premises. Generally, you will be using in all probability the drives which are greater than 50 kilowatt capacity. This is because if you look at single phase, the single phase AC waveform will be somewhat like this. This is what is the single phase AC waveform. When I rectify this particular single phase AC, I am going to have the rectified AC somewhat like this. So I'm going to have, even if I use a simple diode rectifier, I'm going to have, this is the kind of waveform we are going to have for the rectified voltage. So this is the AC input to the rectifier. This is DC output from the rectifier. So if I am talking about a rectifier feeding a DC motor drive, this is the kind of waveform I'm going to have. So because of this, if I look at the current will also have oscillations somewhat like this, depending upon what is the kind of armature inductance the DC motor drive has, and what is the kind of filters and other things that you have employed in the motor drive. This is going to be the current waveform. So this is the rectified voltage. Okay. And this is going to be the current. I'm showing that as the armature current IV. And in a DC motor drive, especially if we are talking about separately excited DC motor drive, we are going to have the torque being proportional to TE is going to be proportional to IA. If I assume excitation is a constant, if excitation is constant, that is field current is a constant, in that case, the torque is going to be proportional to the armature current. So if the armature current is continuously fluctuating, then the torque will also fluctuate. So if I try to draw what kind of torque I'm going to have, the torque waveform will also be fluctuating somewhat like this. So this is going to be the TE waveform. How TE changes, this is how it is going to change with respect to time. What I'm plotting is with respect to time. So if the torque is oscillating, You are going to have again, just like how you say F equal to MA in the case of a linear or translational motion system. For a rotational system, you can say dE is equal to J multiplied by d omega by dt, where d omega by dt is the angular acceleration. So we are going to have, if T is not a constant, if that is going to vary on a continuous basis, for a given inertia, the speed will not be a constant. You will either have acceleration or deceleration on a continuous basis. So we will see that whenever there is a fluctuation in the torque value, you are going to have fluctuation in the speed value as well. So speed will fluctuate if the torque is fluctuating. And if speed is fluctuating, in that case, you would feel a lot of vibrations in the shaft of the machine itself. And the shaft is ultimately coupled to whatever is your load. For example, if it is an electric vehicle and to the axle, if this shaft is coupled, then you are going to see that the journey is not going to be very comfortable within your vehicle because continuously there will be vibration and you will feel, not so comfortable within the vehicle itself. And another thing is, if it is like a textile industry, you are going to see that the fibers are not really fed at a constant rate. So the weaving ultimately done, what is done, it is not going to be really good. So the cloth output which is coming out of the textile industry is not going to look as good as it should have looked. So you will not have a good quality output. The same way, if it is like a tire industry, you are going to see that the threads are not uniform. So the quality of the product, what you get, if it is a printing press, for example, the printing is not going to be done in a uniform manner. One line can be printed on the top of another line. So you may not be able to read the book at all if you are having vibrations in the motor shaft, which is running the printing press. So in general, in single phase case, because you are going to have oscillations in the torque and oscillations in the speed, due to which vibrations will be there in the shaft, the product quality will not be good, especially at larger ratings. Even smaller vibrations can cause cracks in the shaft. So it could be detrimental to the life expectancy of the drive as well. So that is the reason why, if you look at three-phase, in three-phase case, we will be looking at this in greater detail at a later part of this course when we are talking about three-phase DC motor drive. So in that case, you would see that there will be 6 pulses that are produced within one cycle. So 6 pulses which are produced within one cycle will look somewhat like this. So this will be the three-phase rectifier output. Because of which, if you look at the oscillation, here in single phase case, the oscillation is equal to whatever is the peak value of the voltage. If the peak value of voltage is Vm, I'm going to have the peak value of the voltage as the complete ripple content that is present in single phase voltage, output voltage. Whereas in this particular case, it will be much smaller than that. So the ripple is only this much in the case of a three-phase. So this will actually call for the current also being almost a constant. So the current could be almost a constant. So you may see that the current is somewhat like this. So you can say the average value of current is very close to whatever is the ripple that you observe also. So if you have a sufficiently small value of inductance, even that is good enough to make this current ripple free. So the torque will be somewhat constant in the case of three-phase drive. And the speed will also be a constant. And that is one reason why generally you're going to see that the three-phase supply is generally employed in most of the industries where the total load capacity is greater than 50 kilowatt. Whereas single phase is employed in most of the industries, which are small scale industries whose load will be anywhere close to 10 kilowatt or even lower. But single phase is employed only in one case as an exception where the capacity is greater than 50 kilowatt. So one exception for this generalized rule is electric traction system. So for example, if you look at the suburban train service that we use, like metro rail, or if you look at Rajdhani trains, which are flying between Delhi and Chennai or something like that, it is covering almost 2000 kilometer of distance completely. So if you are looking at 2000 kilometer distance, then if you use single phase AC, all you require is only one overhead line. And you're going to have the rail at the bottom. The rail is going to serve as the return conductor. So this is the rail. So the rail will serve as the return conductor. And this is the overhead single phase line. And you are going to have the train essentially running between these two. And you will have generally a conductor which is collecting electricity from here. So this overhead conductor which is collecting electricity from here. So these are the different units of this train. And they are all collecting electricity from the overhead line. Okay. So it is collecting. So in this particular case, if it is single phase, you need only one conductor to carry electricity throughout this 2000 kilometer. But if it is three phase, you will require three conductors minimum to carry three phase electricity through this 2000 kilometer. So single phase results in saving of copper conductor. Whereas if it is three phase, you definitely have to incur a lot of expenditure on installing this three-phase transmission line throughout this 2000 kilometers of distance. So only one exception for this kind of single-phase usage for greater than 50 kilowatt capacity is electric traction system, where you are going to have the complete railway running through the train running through electricity. So single phase electricity will actually save on the copper, the amount of copper that is being spent while installing these lines, electrical lines. So when you make a choice of the electric drive, the first and foremost thing we need to look at is what kind of power supply is available. And based on the power supply, you are going to look at what kind of converter you are going to employ so that ultimately it will feed the motor properly. So if it is a DC motor and the power supply available is AC, then you have to use a rectifier, controlled rectifier or controlled rectifier. If it is going to be AC motor, depending upon whether we want a very wide range of speed control or whether we want only a short range, we may use just voltage control or voltage and frequency control, like what I mentioned in the last class. So if you are using voltage and frequency control, then what you will require will be an inverter. If you need only voltage control, then you will have a voltage controller. Only magnitude of voltage can be adjusted. AC voltage controller will be good enough for this purpose. Okay. Now, if we have decided now on the power supply and converter based on what kind of motor we are going to use, again, the motor choice also depends upon what kind of duty you are going to have for the load, what kind of duty the load is really expecting. For example, if you are having an induction motor probably employed for a boiler feeder pump. So in a thermal power station, the boiler will be continuously fed with water. So boiler feeder pump is the one which is actually feeding the boiler with water. So if the water is being pumped using an induction motor, in all probability, this will work 24/7. As long as the power station is working, you are going to have 24/7 duty for this particular motor. And the amount of water that you are going to pump, this will be almost constant. So the power demand in all probability will be a constant. You are not going to really require variation in the speed and torque. So this will also be a constant. And we may not require multiple start and stop. Only once if you start, maybe it is good enough. It can keep running for the entire duration of the power station's working. So no multiple start and stop. That is not needed. So because of which, when I choose a motor for this particular application, all I need is how much is the water output I require. Accordingly, I will calculate how much is the power that is required for the motor, and I'll choose a motor of that particular capacity, be it a DC motor or be it an AC motor. Whereas, if I am looking at a load like an electric vehicle, if I am looking at a load like an EV, obviously, you're not going to run the vehicle continuously. If you see a red light on the road, you have to stop. If you want to avert an accident, you have to stop. So you will definitely have multiple start and stop. So when you are starting, the current drawn may be very high for your machine. And similarly, when you are stopping, again, you may employ regenerative braking. Again, the current through the machine may be somewhat larger. So these will really require very good transient operation also for the machine. So the machine should be able to deliver not only a good steady state operation, but transient operation also should be, transient performance also should be very good. This is one thing. And another thing is, in an electric vehicle, if you look at the specific application, whether it is a metro rail kind of application or if it is a regular car which is going on the road, the speed ranges generally are very large. The speed ranges are large in this particular case. Whereas if you look at a pump kind of application, speed range may be limited. We will not really have a very vast speed range. So the speed range here will be limited. So if we are talking about a car or especially race car, normally you might have seen that many of the IC engine vehicles have 4 gears, but race cars can have up till 5 gears. So you are going to have really a large amount of speed variation, which means we have to have very quick response for the drive. So here we should have quick response for the drive, and it should be able to vary from minimum to maximum speed in a very, very short duration. It should be doing that in a very short duration. So 2 or 3 things come out here. One is, depending upon the load, you will decide what is the kind of speed range your drive will be able to give. And especially in a particular application, something like a race car, you will require a vast speed range and very quick response also. And we may require multiple starts and stops, and transient performance should be good. So all these things also tell you that we should look at the inherent capability of the motor and the capability of the drive along with the control. Both have to be looked at before really when we employ a particular type of electric drive for our application. Another thing we might have to look at is overload capability of a particular motor drive. So what do we mean by overload capability? To understand this, let us say normally I can lift a weight of 10 kg. But if I am asked to lift a weight of 15 kg, maybe I can do it for 10 seconds. I cannot carry it for much longer duration. 10 kg, maybe I would be able to carry on a continuous basis. Whereas if I am asked to carry 15 kg weight, I may be able to carry it for say 20 seconds. Whereas if I'm asked to carry 20 kg weight, it is probably possible for me to carry it for 7 seconds or 8 seconds, nothing more than that. So I would say if this is my full capacity on a continuous basis, this is essentially 150% overload when I'm talking about 15 kg, whereas this is 200% overload. So similarly, if a particular motor is rated for, let us say, 5 kilowatt, it may be able to deliver 5 kilowatt. I can say probably it is something like, 5,000 divided by, if it is a normal speed of 1000 RPM or so. So roughly I'm going to divide it by 104.7 radians per second. So this is going to give me approximately 50. So I can say approximately 45 or 50 Newton meter torque. So normal torque is going to be 45 or 50 Newton meter at 1000 RPM speed. So for a short duration, it may be able to deliver until 90 Newton meter, which is 2 times full load torque. So how much I'll be able to overload my motor even for a short duration? This is what I call as the overload capability of the motor. So for example, if it is a DC motor, we already said that the torque is proportional to IA. So the armature current is going to essentially decide how much is the torque deliverability of the machine. So unless I increase the armature current to twice the rated value, I will not be able to deliver twice the rated torque from this machine, even for a short duration. One major problem normally you see with the DC machine is its commutator. The commutator and brush assembly is a very intricate structure. It is going to have very intricate structure. So what actually this commutator comprises is that it will have one copper segment which is separated from the next copper segment by a mica. And again, there will be some mica, another copper segment. So this is going to actually make the entire arrangement of the commutator. So this is how it is going to be. And you would see that a brush touches this copper segment and it is collecting the current. So this is the way generally commutator brush assembly works. Let me try to see whether I'm able to find a commutator and brush assembly image. So you can see what is shown here. Okay, so let me try to show this. So you can see that this is the commutator. This is going to have one copper segment. Right next to that, there is mica, then another copper segment. This is the brush. This brush is actually collecting the current from the copper segment. And these are the rotor conductors, rotor coils, which are actually being welded ultimately to the copper segment of the commutator. So you are going to see that because of its intricate structure, if the current becomes extremely high, if current becomes 2 times the rated value, the contact area between the copper segment and the brush may not be sufficient enough. So there could be sparking that can happen between the copper segment and the brush. So if this is the copper segment and the brush is actually collecting the current from the copper segment, so this is the area of contact where these two are contacting each other. So that can handle only certain amount of current. If the current exceeds around that also, there will be ionization of the air. So you will have sparking happening around this. So in the case of a commutator, in the case of a DC machine, the commutator arrangement is the limiting factor as far as the current is concerned. So generally, the overload capability of a DC machine at the most is 2 times the rated torque or 2 times the full load torque at the most, nothing more than that. Even this is generally the outer limit as far as the DC machine is concerned. Whereas in an induction machine, if you may recall what we drew as the speed torque characteristics of an induction machine, we are going to have TE here. What is the electromagnetic torque developed by the machine? And let me draw the speed on this side and TE on the other side. So this is going to be the speed and this is going to be the torque. So you would see that at synchronous speed, the torque is 0. It reaches a maximum and then it comes down to the starting torque at speed equal to 0. So this is the starting torque. And this is going to be the maximum torque. And generally, the maximum torque is going to be about 2 to 2.5 times T full load. So we would be able to say this is T full load. This is the maximum rated torque. Then the maximum torque is anywhere between 2 to 2.5 times. So I would say overload capacity of the DC machine is only twice at the most, whereas induction motor, it can be as high as 250% of rated torque. And in the case of synchronous machine, we are going to have generally the equation that actually corresponds to the synchronous machine's power is 3 EV divided by XS sine delta, where delta is the load angle. So delta is the load angle, which is the angle between excitation voltage and the applied voltage. So this is going to be the load angle. And we are going to have XS as the reactance or synchronous reactance of the machine. And we are going to have delta normally around 20-25 degrees, nothing more than that. So because of which the maximum torque or maximum power capability of the machine is determined when delta is equal to 90 degrees. So when delta is 90 degrees, we are going to have the maximum power deliverability for the machine. So you can say the overload capability of a synchronous machine. What is the maximum torque or maximum power that can be delivered by the synchronous machine vis-a-vis its normal power, which is corresponding to about delta equal to 20 or 25 degrees. So this is corresponding to rated condition. So we should be able to say that it is 1 with a sine 90 divided by sine 25 degrees, for example. So this is essentially 1 divided by whatever is sine 25 So that will be maybe slightly even less than 0.5, maybe 0.4 or something like that. So that is going to give us about 2.5 times. So the overload capability of a synchronous machine is also almost 2.5 times that of whatever is its full load capacity. So three factors what we actually looked upon as making a choice for the electric drive. We said first is power supply. We already talked about it. Then the converter, what kind of converter we are going to use for feeding the motor. And the third thing is what kind of duty we have. What we mean by duty is what is the range of speed, what is the range of torque, what is the kind of overload capability. So speed range again depends upon what kind of application we have. I already told you that electric vehicles will require huge range of speed. Some of the applications like lens adjustment in a microscope, they will require only very small range of speed and with very small value of speed also, small magnitude as well. For example, in the case of microscope lens adjustment. Or let us say if the tool has to be adjusted in a lathe, those also can be actually adjusted at a very slow pace. So you don't require really a large amount of speed at all. Whereas if I am looking at, for example, a high speed centrifuge, which is used to extract a small amount of precipitate from a large amount of liquid. These are specifically used in some of the chemistry laboratories or biotechnology laboratories. So high-speed centrifuges generally will run at hundreds of thousands of RPM. So 100,000 RPM or more. So in those cases, definitely the speed that can be offered by the motor drive has to be very high. So if you look at induction motor or synchronous motor, generally the speed is given by 120 F by P. And even for a pole of two-pole machine, you will get maximum 3000 RPM for 50 Hertz supply, nothing more than that. So you are going to have a limitation of the speed in the case of induction motor and synchronous motor if you are using directly the power available from the grid. Whereas DC series motor can give extremely large speed without any power converter. So DC series motor is generally the natural choice whenever you are going to require very high speed. So typically, if you look at a food processor, mixer, all of them run generally at 10,000 RPM or 15,000 RPM. In those cases, what you use is a series motor, but the series motor can work on both AC and DC. So we call that as universal motor. So the universal motor typically is used in hand drills or food processor. So this is essentially a series motor which can run on both AC as well as DC. So we call this a series motor. So typically, depending upon the application, you will make a choice of your drive. The application might require extremely large speed range. It might require only a small speed range. It might require extremely high speed. It may require multiple starts and stops. It may require extremely good transient performance. So all those things will be, dictating what kind of drive you want to choose for your particular application. Another important constraint, I think we talked about four typical constraints. The fifth constraint that I want to talk about is what is the kind of space that is available for your motor drive to be put in or installed in. So space and weight limitation. If we are talking about, for example, aerospace drive system, we are extremely worried about how much is the weight that can be lifted or that can be put on board in an in a flight. So aerospace drives are generally designed at high speed. So whenever we talk about high speed and high frequency, then for a given power level, the power level is decided by speed multiplied by torque. So for a high speed, torque could be lower. For a high speed, torque could be lower for a given power level. So if the torque is lower, the flux also could be lower. If the flux is lower, in that particular case, you can say for a given flux density, the area of cross section could be lower. The flux density is basically the material property. So area of cross section could be lower if the flux is lower, because of which you would normally see that we would see that the machines are of smaller size if they are operating at higher frequency. So most of the aerospace drives operate at high frequency to reduce the size and weight. Another typical example is electric vehicle. Again, electric vehicle, we have very limited space because you have to have sufficient passenger space. So this on the bonnet, you are going to place the motor in all probability in the front of the vehicle. And in the front side, the space available is limited because of several other auxiliaries that are sitting in the car, like cooling arrangement has to be there, infotainment has to be there. There should be display, there should be a dashboard. For that, there will be a lot of electronic circuits which are going to show the display. So you will have very limited space for the drive unit. So again, the weight should be as limited as possible so that you don't have to haul a huge amount of weight of the motor and the drive unit also. So in an electric vehicle, again, the space and weight both have to be as small as possible. The space occupied by the motor drive as well as the weight of the motor drive, it should be as small as possible. Battery itself is going to be pretty heavy. So if we do not increase the weight of the motor and drive, then that will be much better for the entire design of the electric vehicle. So again, we have to choose our motor drive in such a way that its weight is smaller, its space occupied is also smaller. Whereas when we are talking about employing a motor drive in industrial drive, at least we will have sufficient space. So we don't have to worry too much about the space availability and weight of the drive itself. We don't have to worry about that much. So space and weight limitations are another major thing that we need to worry about when we make a choice of the drive. So the 5 factors what we considered basically in terms of choice of a drive are: one is power supply. The second one, what we talked about was converter. The third one is range of power, speed, and torque. The fourth one that we talked about was the overload capability. And the fifth one, what we talked about was space and weight limitation. So these are the five factors that we need to consider. Of course, transient performance, how quickly the drive responds to the needs of the driver in an electric vehicle, or to the needs of an operator in any industrial drive. These are also extremely important. When we talked about the advantage of an electric drive, we said they are capable of delivering 4-quadrant operation. So what do we mean by 4-quadrant operation of a drive? So let us try to talk about this pertaining to a lift or an elevator. What is an elevator mechanism? First of all, you have to understand that before we talk about the 4-quadrant operation. An elevator mechanism is going to have a cage in which generally people might get in. And it will have a rope which is actually hanging this cage through a pulley. So let me probably draw it a little better. So I'm going to have a pulley here. And this pulley is going to be connected to a motor through a shaft. So the pulley is rotating in one way or the other, depending upon whether the cage is going up or down. Now here is going to be a rope. The rope will be made up of, in all probability, some kind of metal fiber. So this is going to have the cage on one side, which is going to have people getting in, and you're going to have a counterweight on the other side. I'm going to show the counterweight somewhat like this. So this is counterweight. And this is going to be the cage. And through this shaft, it is going to be connected to a motor. So I'm going to show the motor here. This is going to be my motor, which is rotating this particular pulley in one way or the other. Now, generally, empty cage weight, the weight of the empty cage will be less than that of the counterweight's mass. The counterweight is going to have a higher weight than the empty cage. But when people get into the cage, it is going to become heavier as compared to the counterweight. So this is the general mechanism of this particular elevator. So now that we know the basic mechanism of the elevator, let us try to look at the 4-quadrant operation. So this is going to be speed. Speed is along the y-axis. And we are going to have the torque along the x-axis. So what is the kind of torque demand we require? That torque demand is going to be set by the load. So that becomes an independent variable. We don't have any control over it. Whereas the speed at which we run the motor, that is completely in our hands, depending upon what kind of control we have for this motor. So that is why it is along the y-axis. So this is a dependent variable that is dependent upon how we implement the control, whereas the torque is an independent variable. So let us say there are a few people who have got into the cage and they want to go up. When they want to go up, this cage is going to be heavier than the counterweight. So the gravity will automatically pull it down. So unless I generate a torque in this direction so that the cage is taken up, I'm not going to be able to move the cage up. So when a loaded cage is going up, when a loaded cage means where people are sitting inside. So loaded cage going up. We are going to have actually the torque produced in this direction the speed also in this direction. So both are going to be aiding each other. When the torque and speed are aiding each other, we call that as motoring. And we are assuming that the clockwise direction of rotation, generally we call that in this particular case as forward direction. So we call this as forward motoring. So forward motoring is when the torque as well as speed both are in clockwise direction. Whereas, let us try to look at what happens in the other case. The speed is positive, whereas the torque is negative. So which means I'm going to have this as the speed, whereas the torque is going to be in the opposite sense. So I'm going to write this like this. TE is in opposite sense, whereas omega is in clockwise sense. And what happens under this condition? When will such an operating condition exist? Let me try to draw the cage also here. Cage is having people and the counterweight is on the other side. So cage has to be lifted up against gravity when we are talking about quadrant 1 operation. Quadrant 2 operation, when we are having, let us try to see what kind of situation will warrant this. So the speed is in this particular direction, which means in all probability, even without any stimulus from the motor side, the cage would be able to move up. That's what it means. That means the cage in all probability should be empty. So I have to have the cage to be empty, whereas the counterweight will automatically pull it up because counterweight's mass is going to be higher than the empty cage. So let us say I want the elevator to come to the 5th floor and I'm standing in the 5th floor. I want to go down and the elevator's cage is empty. So it has to come up. So when it gets the command that it has to come up, automatically the counterweight will be able to pull it up without any problem. The motor does not even have to impart a torque in the clockwise direction. So if it automatically comes up, it can go and hit on the ceiling. This particular cage can hit on the ceiling. So to avoid that, you have to develop a torque. The motor has to develop a torque in the counterclockwise direction so that it moves at a controllable pace. It doesn't move because of gravity. It doesn't move at a very, very fast pace and go and hit the ceiling of this particular elevator arrangement. So this is braking because you are going to have the direction of movement is forward, but the torque and speed are in reverse direction, opposite of each other. So we call this as forward braking. On the other hand, if I'm going to have the pulley sitting here, and let me see whether it is empty cage or it is with people. So let me draw this also, counterweight also on the other side. Here speed as well as torque both are in opposite direction. So I'm going to have the speed also like this and torque also like this. So this is going to be TE and this is going to be omega. Both are in opposite sense. Okay. So when do we need really a torque to be developed in the opposite sense compared to the normal forward movement to aid the motion in the opposite sense, in the reverse sense itself? So if this is an empty cage and the counterweight's weight is higher, the normal position, normal way of movement would be only upward. It cannot be downward. But what we want is a downward movement. Maybe I am sitting, standing in the ground floor. I want to go to 6th floor and I'm calling the elevator cage to come down and it is an empty cage. So it cannot come down on its own because its weight is going to be less than the mass of the counterweight. So specifically, a torque has to be developed in the opposite sense that is in the counterclockwise sense, to bring down the cage. So this is empty cage coming down, because somebody in the ground floor has called for the elevator cage. So this is both torque and speed aiding each other, but they are in the reverse direction. So we call this as reverse motoring. Obviously, the fourth one is going to be reverse braking. And I'm sure you can figure out under what situation reverse braking happens. So in a very, very simple mechanism like an elevator, you would require all four quadrants of operation to be implemented properly. And you would require braking torque to be developed on and off, depending upon whether we are moving an empty cage up or down, or whether we are really moving, loaded cage up or down. So elevator definitely requires all the four quadrants of operation. It goes without saying that we will require similarly all four quadrants of operation even in the case of an electric vehicle, because very often you may brake to avert an accident, or if you encounter a red light, you have to brake. Or even if it is a train service, if you encounter a station, you'll have to stop. So for which you have to incorporate braking. So four quadrant operation can easily be implemented in an electric drive system as compared to many of the other types of drives like hydraulic drive or mechanical drives. So having seen the basics of electric drive system until now, we are going to look at the dynamics of load system in the next class. So we would be looking at the actual course content starting with dynamics of load system in the next class.